Hi everyone, we're going to start with chapter 4, probability for discrete variables. So what's going to happen is I'm going to just go through the lesson. I've already filled it out. What you can do is pause the video at any point, fill in what you need to fill in, and then there's the questions that are going to follow. So for today's lesson, it's 4.1 and 4.2. I'll highlight the important pieces of information and we'll go from there. So this 4.1 is probability distribution. It's just basically a way of displaying probability, the outcomes of your probability. So the two definitions I want you guys to focus on is this discrete random variable versus the continuous random variable. A discrete random variable is a variable that assumes a unique value for each outcome. Basically, what it is it's whole numbers. So the roll of a dice is either 1, 2, 3, 4, 5, or 6. There's no other numbers, there's no other possibilities. So in those cases, that's a discrete random variable versus a continuous. A continuous is a variable that assumes values from an infinite number of outcomes. So the example here is 1's height. My height could be 6, 1, and 0.235789 inches. So there's an infinite number of possibilities. So height, somebody's weight, numbers that are continuous, that's what a continuous random variable is. Okay, so there's going to be a couple of questions. It's just ask you to differentiate between the two. Okay, so we just go into this investigation. The investigation is just, they're called Sichermann dice. They're six-sided dice, but they have different numbers. So this table was created just like we have regular dice from 1 to 6. We create a table for all the outcomes. So what happens on dice 1 and dice 2, I just filled in the table here. So you can quickly do that on your own. Basically what you find out is that the distribution of the numbers of the sums follow the same pattern that a normal 1 to 6 dice would show. No big deal, just another example. Okay, so the random variable in this case is just what the sum of the dice comes out to be. And this is discrete. It's discrete because the outcome of the dice is anywhere from 2 to 12. That's a definite and distinct number. Okay, so this is a discrete type of random variable. So what I do in this scenario is I'm going to construct a probability distribution and then a bar graph associated with that. So when we go to the distribution, I look for the sum of the two dice being as 2. That happens one time. So 1 out of the 36 total is a 2. The 3s, you'll see there's 2 of them. So 2 out of 36, the outcome is a 3. And so on and so on and so on. You'll see that the probability of rolling anywhere from 2 to 12, it follows the exact same as a 1 to 6 dice would. Okay, so then I just take that to a bar graph, a very simple bar graph. On the y-axis, I have probability. That's different. So that's why this is called a probability distribution. I just put 1 out of 36, 2 out of 36, 3, 4, 5, 6, and then the sum of the dice here, and I just make a nice bar graph, and you see how the probability is distributed. So you'll see that the 7 comes up the most and it falls off on both sides. Okay, so that's the idea of a probability distribution. There's a couple of textbook questions that follow that up. Okay, so for this section for 4.1 on page 151, number 1, and 152, 4B and 6AD, just a few questions. So that's what you're going to submit in today's piece along with 4.2. Okay, so let's move on to 4.2 really quick. So 4.2 is a specific type of distribution. It's called uniform distribution. Uniform meaning all the same, just like you guys have your school uniform and so on. So this is a distribution where all outcomes are equally likely. So with the Sichermann dice, it wasn't equally likely. The 7 came up the most, the 2 and the 12 came up the least. So those weren't equal, and you saw in the graph. These ones in this graph, you're going to see all outcomes are equally likely. So here's the example. A calculator has been programmed to generate a number between 1 and 5. Classify the distribution. So this is going to be a probability distribution. Calculate the probability distribution on the table. So I did that here. the outcome being 1 to 5. They all have an equal 1 out of 5 chance of being selected. I'm now going to convert that to a nice decimal 0.2, just easier to graph. It's easier to graph 0.2 than 1 out of 5 or 1 over 5. It's easier to do decimals rather than fractions. Okay, sketch a graph. So the outcome of 1 to 5, the probability, I just used the short form there, probability of x happening. This is the x axis, obviously. So that goes up to 0.2. You just square off the bar and shade it in, meaning they're all equally likely. Okay, and then the next piece says calculate the expectation. Sorry, let me go back to the last one. The bottom part, the expectation stuff, we're not going to cover it. If we get back into the school, we'll go over it. But at this point, I'm just going to try to give you guys the most important pieces of information. So right now, as of now, that just doesn't come into play. Okay, but this one is easy to do, this expectation, and interpret the meaning. So if I go here, basically the expectation, if you're picking numbers from 1 to 5, the expectation just means what on average do you expect to get or roll or for the generator to pick. So simple way of doing that is you add up all the outcomes. You can get a 1, 2, 3, 4, or 5. There are 5 different outcomes. When you total up the top, it's 15 divided by 5. So you have an average of 3. And that should be pretty obvious. If you're picking numbers between 1 and 5, the average number is going to be 3. So there's just a quick way of calculating that, nothing too difficult. Okay, and this leads into the expectation with a game. If the expectation for the game is 0, I'm just going to highlight that, then the game is fair. It's a fair game. So if you're playing at a casino, if you're playing on a game show, if wins and losses equal each other, the game is fair. If not, it's not a fair game. Okay, so here's the example for today. A game involving rolling a dice. A player who rolls an even number receives points equal to 2 times the number. If you roll an odd number, you lose 3 times the value of that, whatever you roll. Is this game fair? Okay, so let's talk about the wins first. You win or you get points if you roll an even number, a 2, a 4, or a 6. The game says that if you roll a 2, we're going to double it, so you're going to get 4 points. If you roll a 4, we're going to double it, you're going to get 8 points. If you roll a 6, we're going to double it, you're going to get 12 points. If you total up those points, you get plus 24. If you go to the losses column, a 1, 3, or 5 is considered a loss. If you roll a 1, you lose 3 times the points. So you're going to be minus 3. Roll a 3 and triple it, you're going to be minus 9. If you roll a 5 and triple it, you're going to be minus 15. When you total those up, you go minus 27. So therefore, this game is not fair because the pluses and the minuses don't equal 0. You're going to lose more often than you win. Okay, so this is not considered a fair game. There's a couple of questions today that are going to ask you, is it a fair game or not? Okay, so on page 157, 1 to 4, a couple multiple choice in there, nothing too difficult. Page 158, 7, 8, and 11. You have to do your own distribution table about a uniform distribution. Okay, so that should be a very easy way to introduce the unit. Tomorrow is 4.3 and Thursday is 4.4, and that will be it for chapter 4. In addition, I'm going to try to get the Nelson textbook available for you guys online. For now, what I'm going to do is I'm just going to show you the pages, just in case I can't get it up properly. I'm just going to show you the pages, pause the video if you need to. So here we go. The page 151 looks like that. So you're required to just do number 1. It's right there. And you're going to be doing, on this page, you're going to be doing 4B, which is right there. Draw a probability histogram for each of the distributions. 4B is right there. And then 6A to D, we have a distribution table about some marbles. And then you're asked some various questions related to that. Okay, so that's the first section. Now we go to 157, page 157. You're going to do 1 to 4. So here is, sorry, let me get that out of the way. 1 to 4, there's 1, 2, and 3. Some easy multiple choice there. And there's number 4, a jar containing some balls. And then 7, 8, 11. There's 7. 8, and 11 is like a game show question. Okay, good luck, guys, and we'll talk to you tomorrow.